Hello everyone. Thank you for joining me today. I'll be presenting on an exciting topic: Ethereum request for comment ERC 4337 code analysis. Today, we'll be exploring the world of account abstraction in Ethereum, diving deep into the ERC 4337 specification. Here's our agenda for today. We'll start with a brief introduction to ERC 4337, followed by an overview of the code framework. We'll then discuss each of the key phases: the user signature phase, relay phase, and final execution phase. After that, we'll look at the different modules and functions involved. Then focus on the entry point smart contract, and end with a discussion on the feasibility of wallet verification. Before we start, I'd like to talk about a vibrant and dynamic community called DoraDojo. DoraDojo is an open-source knowledge community focused on cutting-edge technologies such as encryption and Web3, co-built by hackers. DoraDojo regularly organizes and shares sessions in the form of live broadcasts, audio, and text. The topics covered include L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. Some of the specific topics covered include Scroll/Polygon zkEVM, Eigen's hybrid proof system, Starkware, Aztec, Optimism, Zkri, Aptos, Move, cryptography, including zero-knowledge proof, public key encryption, hash functions, and lattice ciphers, distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communication and spacecraft system design. The DoraDojo community is constantly expanding and inviting new members to join. If you are interested in learning more about cutting-edge technologies and staying ahead of the curve, I encourage you to contact Dojo at DoraDojo0 on Telegram and claim your bounty. The dojo welcomes proposals for new content, and they will fund and share it. So, whether you are an experienced developer or just starting out, DoraDojo is the perfect community to learn and grow alongside like-minded individuals. Join us today and let's explore the world of cutting-edge technologies together. To start, let's talk about ERC 4337 in the world of Ethereum. Account abstraction has become a vital concept, and ERC 4337 is at the forefront of this development. But what exactly is account abstraction, and why is it important? Account abstraction allows us to separate the control and logic of accounts from the core protocol of Ethereum. In simpler terms, it means that users can have accounts that behave more like smart contracts, rather than being limited to the default account model that Ethereum originally provided. This opens up new possibilities for how accounts can be managed and used on the network. For example, with account abstraction, we can implement features like multi-signature wallets, social recovery wallets, and even fee payment with tokens other than ETH, all without requiring changes to the core Ethereum protocol. This flexibility is crucial for enabling innovative user experiences and addressing some of the limitations of the current account system. ERC 4337 is a specification that provides a framework for achieving account abstraction using a new type of transaction object called a user operation. This object allows for more complex logic and custom verification steps, making it possible to implement advanced account features. The great thing about ERC 4337 is that it achieves this without modifying the Ethereum consensus layer, which makes it highly compatible and easy to adopt. So, why is this important in the Ethereum ecosystem? The Ethereum community has long recognized the need for more flexible account management. As decentralized applications become more sophisticated, users require more control and customization over their accounts. ERC 4337 addresses these needs, making Ethereum more user-friendly and adaptable to diverse use cases. In summary, ERC 4337 represents an important step forward for Ethereum, enabling account abstraction and enhancing the flexibility and functionality of user accounts. This lays the foundation for a wide range of innovative applications and improved user experiences on the Ethereum network. Next, let's take a look at the overall code framework for ERC 4337. This framework plays a vital role in achieving account abstraction in Ethereum. ERC 4337 introduces a structured process to handle user operations in the Ethereum ecosystem. The key components involved in this process are illustrated in the diagram here. Key components and their roles. The user initiates the process by creating a transaction. This transaction is referred to as a user operation. The bundler collects multiple user operations from various users. It serves as an intermediary, preparing the transactions for submission to the blockchain. The validator checks the authenticity and validity of the user operation. This ensures that only legitimate transactions proceed further. The paymaster funds the transaction if the user doesn't have enough ETH to cover the gas fees. This component allows for flexible payment options. The entry point smart contract manages the user operations and coordinates the execution process. It serves as the main gateway for the user operations. As shown in the diagram, the process starts with the user transaction phase. The user's operation is created and sent to the bundler for verification. The user creates a transaction. The transaction is structured as a user operation. The bundler collects and verifies the user operation. It ensures the transaction is valid before forwarding it to the next step. The user operation is validated by the validator. This step ensures the transaction is legitimate. The entry point executes the user operation. This is where the transaction is actually processed on the blockchain. The paymaster settles the payment for the transaction if necessary. The transaction is finalized. In summary, the ERC 4337 framework provides a clear and structured approach to account abstraction. By utilizing components like the bundler, validator, paymaster, and entry point, it allows for efficient and flexible transaction processing. This framework is crucial for enhancing user experience and enabling innovative applications in the Ethereum ecosystem. Below is an example of code snippets that align with the various phases and components involved in the ERC 4337 framework. The user operation structure is central to the framework. This struct represents a user-initiated operation. The bundler is responsible for collecting user operations and submitting them to the entry point contract for validation and execution. The validator checks the validity of a user operation. The entry point contract is the core contract that manages the user operations and coordinates the execution process. Next, the paymaster funds the transaction if the user doesn't have enough ETH to cover the gas fees. Finally, putting it all together. Here's an example of how these components might work together. This code provides a comprehensive example covering the key aspects of the ERC 4337 framework, including the user operation struct, bundler, validator, entry point, and paymaster components. Now, let's dive into the user signature phase of ERC 4337. Overview of the phase. The user signature phase is the initial stage where the user creates a transaction and signs it using their private key. This transaction, referred to as a user operation, contains essential details such as the sender's address, a nonce, the call data, and, of course, the user's signature. This phase ensures that the transaction originates from the legitimate account holder. Next, the key operations in this phase involve creating and signing the user operation. This is crucial because the signature serves as proof of authenticity, confirming that the user has authorized the transaction. The user operation struct typically looks like this. Here's an example code snippet that demonstrates the creation and verification of a user operation during this phase. In this example, we first create a user operation by signing the relevant data. Then, we verify the user's signature to ensure the operation's authenticity. This phase is crucial in the ERC 4337 process because it establishes the validity and origin of the user transaction, setting the stage for subsequent phases. Next, let's move on to the relay phase of ERC 4337. The relay phase is the intermediary stage where user operations are collected and submitted for processing. This phase is crucial for aggregating transactions and efficiently packaging them for execution on the blockchain. During this phase, a component known as the bundler takes multiple user operations from the user operation mempool and prepares them for submission to the entry point contract. This relaying process allows the system to handle multiple operations at once, improving efficiency and reducing costs. Here's an example code snippet that illustrates the relay process during this phase. In this example, the bundler contract takes in an array of user operations and relays them to the entry point contract. The entry point contract then processes each user operation accordingly. To summarize, the relay phase is all about preparing and submitting user operations for execution. This phase leverages the bundler component to gather and relay multiple operations, enhancing efficiency. The example code snippet demonstrates how the bundler collects and submits user operations to the entry point for final processing. Moving on, let's discuss the final execution phase of ERC 4337. The final execution phase is the stage where the actual transaction is executed on the blockchain. During this phase, the validated user operation is processed by the entry point contract, which executes the desired function or transfers control to the specified contract. This phase is crucial because it represents the culmination of the user's intent, where the desired actions are performed on the Ethereum blockchain. Here's an example code snippet that demonstrates the execution process during this phase. In this example, the entry point contract takes in a user operation and executes the call data associated with the sender. This effectively performs the desired action. In summary, the final execution phase is where the intended transaction or function is performed on the blockchain. The entry point contract plays a pivotal role in managing this process, ensuring that the user's operation is executed as desired. The example code snippet demonstrates how the entry point executes the user operation, fulfilling the user's intent. As we delve deeper into the architecture of ERC 4337, it's important to understand the roles and functionalities of various key modules. These include the user operation mempool, bundler, and relayer modules. Each of these components plays a crucial role in the seamless operation of the ERC 4337 framework. The user operation mempool serves as a temporary storage for user operations awaiting processing. It is analogous to the mempool in traditional blockchain networks where transactions wait before being mined. The primary purpose of the user operation mempool is to collect and store pending user operations submitted by users. It ensures that operations are readily available for the bundler to pick up and process. Let's take a closer look at how user operations are managed within the ERC 4337 framework, specifically focusing on the interactions with the mempool. The code snippet provided illustrates the essential functionality of adding and removing operations from the mempool. Overview of the code structure. Firstly, let's define what a user operation is within this context. The user operation struct is a fundamental element of the ERC 4337 framework. It contains sender, the address initiating the operation; nonce, a unique number that prevents replay attacks; call data, the data or commands that are executed in the transaction; signature, a cryptographic signature proving the sender authorized the transaction mempool mapping. Next, we have a mapping that stores these user operation structs. This mapping, termed mempool, uses a bytes 32 hash as a key to uniquely identify and access each user operation. This design ensures efficient retrieval and storage of operations. Now, let's look at how a user operation is added to the mempool. In this function, add to mempool, the user operation is passed as an argument. We first generate a hash of the user operation using kecac 256. Which is a cryptographic hashing function, combined with ABI to encode to serialize the user operation data into bytes. This hash, op hash, acts as a unique identifier for the user operation within our mempool. We then store the user operation in our mempool mapping using this hash as the key. Finally, removing an operation from the mempool is straightforward. To remove a user operation, the corresponding op hash is provided, and the delete keyword is used to remove the key value pair from the mapping. This effectively clears the stored user operation, freeing up space and managing the lifecycle of transactions within our system. In summary, this code snippet demonstrates how user operations are stored and managed using a mapping in Solidity, providing a robust mechanism for handling stateful interactions within the ERC 4337 framework. It ensures that operations can be added, accessed, and removed efficiently, which is crucial for the performance and scalability of any decentralized application using this architecture. Relayer modules are often independently developed by other projects to enhance or customize the relaying of user operations. These modules typically customize how transactions are selected, prioritized, and relayed to the entry point, often incorporating specific optimizations or features that cater to different use cases. The user operation mempool, bundler, and relayer modules form the backbone of the ERC 4337 operation handling. Each module has a distinct role, from storing and preparing to customizing the relaying of user operations. Understanding these modules and their interactions is key to grasping the full capabilities of ERC 4337. Here's a detailed script for a presentation slide about the entry point smart contract within the ERC 4337 framework, including a simple code example and an explanation of its role and functionality. I'll be discussing a crucial component of the ERC 4337 architecture, the entry point smart contract. This contract is the central hub for managing and executing user operations in the account abstraction layer. The entry point smart contract is designed to act as the primary interface for all transactions that utilize the ERC 4337 standard. Its main role is to receive, validate, and execute operations that are passed to it by various other components within the system, such as bundlers and relayers. This contract simplifies the transaction process and ensures that all operations adhere to a standardized protocol. The core functionality of the entry point revolves around handling operations, managing their execution, and interacting with other smart contracts. One of the key functions of this smart contract is HandleOps, which processes arrays of user operations. Let's look at a basic implementation of the HandleOps function. In this example, the HandleOps function takes an array of user operation structs as input. This allows the contract to process multiple operations in a single transaction, optimizing network resources and reducing costs. It iterates through each operation and calls an internal function execute user operation, which actually executes the operation. The execute user operation function uses a low-level call to interact with other contracts or execute specified operations. It checks for successful execution and reverts if any operation fails, ensuring atomicity of the batch process. In summary, the entry point smart contract is a pivotal element of the ERC 4337 framework. It ensures that all user operations are processed efficiently and securely. By centralizing the handling and execution of operations, it allows for more robust and scalable designs in decentralized applications. Here is the sequence diagram for wallet verification feasibility illustrating the wallet verification process. This diagram visually represents the flow of data and interactions within the system for wallet verification using the provided function. You can edit this diagram further using the provided link if adjustments are needed. As you can see in the diagram, the process begins when a user submits a user operation to the wallet verification system. This is the initial step where the user's intent to perform a transaction is captured. Once the operation is submitted, the wallet verification system communicates with the blockchain to fetch the details of the wallet associated with the operation. This is crucial for verifying that the wallet details stored on the blockchain match the operation details provided by the user. After retrieving the wallet data from the blockchain, our system performs the core verification logic internally. This logic is encapsulated in the verify wallet function. Finally, the verification status is returned to the user. This immediate feedback ensures transparency and builds trust with our system. In summary, this verification process is integral to our security framework, ensuring that all transactions are executed only after rigorous checks. Let's now explore a critical aspect of the ERC 4337 framework: wallet verification feasibility. Wallet verification is a cornerstone for ensuring that user operations are indeed initiated by the rightful owners of the accounts. This stage of verification is essential for maintaining security and trust in the decentralized environment of Ethereum. Wallet verification in the context of ERC 4337 involves validating that the signature associated with a user operation is indeed from the claimed sender. This process helps to prevent unauthorized actions and ensures that transactions are legitimate and secure. The feasibility of wallet verification in ERC 4337 relies heavily on cryptographic methods, specifically digital signatures. Ethereum inherently supports such verification through its EVM capabilities, which allows smart contracts to verify signatures with high reliability. This makes wallet verification not only feasible but also efficient and secure within the Ethereum network. Let's review a simple example of how wallet verification might be implemented in the entry point smart contract. In this snippet, verify wallet function takes a user operation and uses a helper function recover address to extract the sender's address from the signature provided in the user operation. Recover address computes a hash of the call data to mimic the original data that was signed by the user. It then uses ERC, a built-in Ethereum function, to extract the address from the signature. This address is expected to match the sender field in the user operation if the signature is valid. If these addresses match, the function returns true, indicating successful verification; otherwise, it returns false. In summary, wallet verification within ERC 4337 is not only feasible but is a robust solution that utilizes Ethereum's native cryptographic functionalities to ensure the authenticity of transactions. This level of security is crucial for maintaining trust and integrity in the decentralized applications that operate on Ethereum. As we reach the end of our discussion on Ethereum request for comment, ERC 4337, let's take a moment to recap the vital elements and consider the implications of this groundbreaking framework for the Ethereum ecosystem. We began today by exploring the concept of account abstraction. ERC 4337 introduces a flexible, smart contract-based account model that abstracts away the complexities of transaction validation and execution processes from user accounts, making them more accessible and functional. We delved into the structure of ERC 4337, highlighting its key components including the user operation mempool, the bundler, the relayer modules, and the entry point. Each plays a critical role in ensuring transactions are processed smoothly and efficiently. We discussed the importance of the user signature phase, where transactions begin their journey. This phase ensures that all operations are initiated by the rightful owners, thereby securing transactions right from the outset. Following that, we examined the relay phase, which bundles and forwards operations for execution. The final execution phase we discussed is where the entry point validates and executes these operations, forming the backbone of transaction processing in ERC 4337. The detailed functionalities of the user operation mempool, bundler, and relayer modules illustrate the decentralized yet cohesive workflow of ERC 4337, showcasing how each component contributes to the overall efficiency and security of the network. Finally, we covered the wallet verification process, a testament to ERC 4337's robust security framework, ensuring that operations are not only efficient but also secure against fraud and other security threats. ERC 4337 is not just a technical upgrade, it is a transformative approach that enhances user experience, security, and developer flexibility on the Ethereum blockchain. Its introduction marks a significant leap towards a more accessible, secure, and user-friendly blockchain ecosystem. This protocol empowers users with advanced capabilities while retaining simplicity in interactions, fundamentally altering how we perceive and interact with blockchain technology. For developers, it opens new avenues for creating innovative dApps that were previously constrained by the limitations of the standard account model. Moreover, the impact of ERC 4337 extends beyond just technical enhancements. It is poised to accelerate the adoption of Ethereum by making it more palatable to a broader audience that demands higher security and easier usability from their digital and financial interactions on the blockchain. In conclusion, as ERC 4337 continues to evolve and integrate into the Ethereum network, its potential to drive innovation and adoption in the blockchain space is immense. It is a testament to Ethereum's ongoing commitment to innovation and user-centric development. Thank you for your attention and engagement throughout this session. I hope you found the exploration of ERC 4337 as exciting and promising as I do. The future of Ethereum looks bright with such advancements, and I look forward to seeing how it continues to reshape the landscape of blockchain technology. As we conclude our discussion on ERC 4337, I'd like to provide you with a list of references that have been instrumental in shaping today's presentation. These resources are invaluable for anyone looking to deepen their understanding of ERC 4337 and its impact on the Ethereum ecosystem. I encourage you to explore these works further to gain a more comprehensive insight into the topics we've discussed. These references represent a mix of technical documentation, academic research, and practical guides that collectively provide a solid foundation for anyone interested in ERC 4337. Whether you are a developer, a researcher, or simply a blockchain enthusiast, these resources will assist you in your journey to understanding and potentially implementing ERC 4337. Thank you once again for your attention today. I hope you found this session informative and inspiring. Feel free to reach out or explore these resources for further learning.